1 p.m. Central Time, and I'm your host, Dr. Matthew Richardson. And today, welcome to another stream of CosmoQuest Astro Office Hours. Um, Give me a quick second to finish setting up here, while also verifying that I'm actually streaming. So let's go ahead and navigate over to Chrome. But as you can probably already see, today's discussion will be related to the diameter of Earth. More specifically, we're going to be calculating the diameter of Earth. But before doing so, let's make sure everything is good with our Twitch stream. What I'm really hoping is that my computer can handle what we're going to be doing with it today. I'm going to have some pretty computationally speaking programs that want to use a lot of resources. So hopefully everything works out. And I don't know yet. I don't know if okay, we're live. But I don't have the information that I need, so let's do this. Let's exit. Let's open up a new window. Let's go back in and see if I can get the chat to work for me. I always have this problem, guys. For anyone who's new, who doesn't know, whenever I come on to Twitch and try to see my chat, I always have an issue being able to see it. All right. All right, I think I can now, I'm gonna go ahead and pop out the chat. Okay, that's done. I can get rid of that screen. Let's go ahead and make sure that things are the advertisement shouldn't make sound. Okay, that's good. All right. So let's make sure everything's working. I'm going to quickly say hi to everyone in the chat who's currently there. All right, I can see my comments. Hey, Tom Van Scotter. Hi, Keeper of Maps. Hey, Peter. So I will try to be as quiet as possible for those of you who are at work. Hey, Tom. Let's see who else is here. All right. Keeper of Maps, hi. Even though I said hi to you, but hi again. Hi. Ooh, a new person. Electrical Skateboard. Nice name. Hi. Hi, Michael T. Mayer. And hi, Tom Van Scotter. All right. So, in the past, and I believe we've even discussed it, not really discussed it, but we've talked about it a little bit in the past about how people believe that the Earth is flat. I'm not going to say much about that, but there are some of us who believe that the Earth is flat. And today's discussion is solely aimed at disproving that because we're going to be calculating that the Earth has a diameter. And of course, if it has a diameter, that means that it has, well, in our case, a spherical shape and not so much a circular shape, but a spherical shape because it's a three-dimensional object. So, oh, perfect, you have your headphones on. Good move. All right, so let's go ahead and dive right into it. Give me 1 second, guys. Yes, Peter. So I've actually went over to Slack to look at some stuff, and I can see your comment, Peter. But I'm going to go ahead and close out Slack right now because it too is taking up resources. Hey, Guido. All right, let's go ahead and jump right into it. So the very first thing I'm going to do is navigate over to an image. Let's see. Let's go to scene 2, and what I'm going to do is Google. All right. Let's go ahead and make sure that you guys can see something first. So I need, not that, browser. There we go. And where are you, Safari? There we go. And I think everything should already be formatted properly. So I want an image actually to help us with today's problem. And I'm going to go ahead and type in how ancient astronomers. Let's put no Earth is round. Let's see what images come up. See if I can. I saw an image, and it was a great image for what I want to do. Nope, this isn't it. How ancient astronomers calculate Earth's diameter. And really all I want is the image. It was a great image. Hopefully it's not a fairly complicated image for what I'm trying to discuss here, but it was a pretty good image. Ah, here it is. It's at the very top, actually. And so really they kind of outline on this website I'm about to navigate to. They actually kind of outline how to do the calculation, but not they outline it good enough. But we're actually going to do the experiment ourselves. Here we go. So let's make sure that you guys can all see that properly. Yes, you can. All right. And so, and I've actually done this experiment a long time ago for one of my astronomy labs when I was in undergrad, actually. And the objective here is to use the North Star Polaris in being able to do this calculation. What you'd want to do is you'd want to go to 2 locations on Earth. In this case, in terms of the picture, they picked locations A and B on the Earth's surface. And what they're doing is they're using a device to be able to measure the angle to Polaris at these 2 different positions. Now the key thing is that the 2 positions must share the same longitude. They can be at different latitudes as long as you can see the North Star from both positions. But the same longitude is important. And so we're going to kind of repeat this experiment right now. Now, of course, it's not nighttime where I'm at. And in fact, I'm pretty sure that this stream is being streamed out to many people across many different time zones. Okay, you know what? I just realized something. I'm going to help my computer out here. It's kind of breathing really hard right now, and I just realized I don't even have it. I don't even have the power plugged into it. So let's quickly do that before we move on. Got my nice little handy outlet here, right here behind me, and we are plugged in. And hopefully that makes my computer happy, because I was at 16%, so it should definitely make it happy. All right, let's go ahead and quickly check comments to make sure that everyone's. I am so sorry to hear that, Guido. Um, oh wait, so Peter, are you having issues as well? Let me make sure that the stream is In the green. Okay. The stream appears to be good for me. Alright. I hope everyone else is okay as well, or not having a problem. Okay, it's okay with you, Tom? Alright. Well, I'm going to continue, but if it gets bad, then hopefully, just ask a lot of questions, and of course, I'll answer them. All right, I got 2 people saying the stream is good. All right, let me go ahead and Peter says the stream is fine now too. Perfect. All right, I'm happy to hear that. Well, then Guido, I'm sorry to hear that you're having issues with the stream. Hopefully, it gets better with time. All right, so let's go ahead and let's recreate this problem, right? Now, like I said, we're across different time zones. How can we do this? Well, we have computers, and they have astronomical software, and that's what we're going to do. Today, we're going to be using Stellarium. So let's go ahead and remember, this is the picture that we're kind of getting here. 2 locations on Earth. They share the same latitude, and all we're trying to do, well, also one key thing is that you must know the physical distance between the 2 locations, and they must share the same longitude. And the overall objective is to calculate the diameter of the Earth. All right. So scene 3, which is blank. Let's do this. I'm going to go ahead and copy. So let's delete this scene. I'm going to go ahead and copy this scene. So duplicate. We'll call this scene 3. It's duplicated. I want Stellarium, so I'm going to change this. Let's rename it to Stellarium. And let's actually choose Stellarium for it. And where are you, Stellarium? Right there. All right, and let's modify this so that it'll fit the screen. Perfect. All right, so far so good. Now, I'm kind of worried because Stellarium uses quite a bit of resources on my computer, but hopefully it's smooth for me and it's smooth for you as well as far as me moving things around in the image. All right, so the very first thing we're going to want to do to recreate this experiment is we need to choose two locations on Earth that share the same longitude. For right now, what we're going to do is we're going to choose one location, and I'm going to allow you guys to choose this location. So please, if you're going to choose a location, choose in the northern hemisphere. Not in the southern hemisphere, but the northern hemisphere. Hey, Michael. Welcome. Oh, snow. That's no good for me. Yeah, here in Clarksville, Tennessee, it's beautiful outside. Um, but well, I don't know. You might like snow. Me personally, I don't like snow that much. Hey, Susie. So, guys, we got someplace. Ottawa, Canada. All right, perfect. So, what I'm going to do is we're going to find out what the latitude and longitude of Ottawa, Canada is. Oh, thanks for the correction, Michael, but I got you. All right. So, let's go ahead and navigate back to our browser. Oh, no, that's what it did. That's not good. So it appears that when I duplicate stuff, it kind of changes things for both scenes. So I need to add a new scene. Or better yet, we're going to delete this scene. All right. Scene 3. Delete this scene. Good. We're going to go ahead and add a new scene. And in scene 2, I need to bring back a few things. First off, I need to bring myself back. So let's do that really quickly. Let's see. Display capture. This should be fast. Okay. That's not it. That's not what we want. That's a bunch of craziness on the screen. Oh, video capture. I'm sorry. That's what I wanted. All right. Let's maintain the aspect ratio down below. Now we need to add back the browser. And so that should be Safari. Thank you guys for bearing with me while I make these quick modifications. Here we go. All right. So we need to go ahead and find out where on Earth Ottawa, Canada is as far as latitude and longitude is concerned. Oh, never mind. Keeper of maps beat me to it. So that's in decimal format. I'll break the internet. Let's be a little bit. I don't want it in decimal format. Let's do this. Let's go ahead and type in lat longitude.net. Yeah, that should have what we're looking for. Perfect. All right. No, I want it in terms of I wonder what happens if I do this. I want the one that has all the information. Let's see if this will give it to me, but not like that. Here we go. All right, this works. So if we see along the left-hand side of the page, and my face might be covering some of that information, but the key thing is that it gives us the latitude and longitude, or this DMS lat, DMS longitude. I'm not too sure. Oh, never mind. DMS, degree, minute, second. Got it. Yeah, that's exactly what I want. So that's what we're looking at here. That's what I need. Let's make sure you guys can see it just as well. Perfect. All right. So we're going to go ahead and copy this information down. Or not copy it. We'll just leave it here. Or better yet, we should copy it. Because I want to be able to make sure we're keeping track of what we're doing here. So let's switch scenes. Let's increase that so you guys can see it. And so we're going to choose the location 1 is Ottawa, Canada. And so we have our latitude, which was, and I'm going to go ahead and just quickly cheat here and copy and paste that information. So that was here, so I can just copy and paste this. So back to text. Perfect, and then we have our longitude. And again, copying and pasting is our friend. Makes things so much faster. All right. And for formatting purposes, let's throw those in there as well. And got it. All right, so now that we've chosen the first location, let's go ahead and choose the second location. And so for this particular location, because I want to be able to maintain a longitude, I'm just going to choose a latitude at random. And it's not really so random. I'm just going to choose 5 degrees north in latitude to make it simple. So location 2, we're just going to put, we're going to put unknown for now. But this might be problematic because we need to be able to know the distance between these two locations. Hopefully that same website can be able to do a distance calculation for us. Or maybe we can do it ourselves, but then that would be cheating. So we're just gonna do 5 degrees more. So 50 degrees, 25 minutes, 31.9-ish seconds. All right, perfect. So these are the 2 locations that we want. Let's go ahead and calculate the distance between them. So let's see. Let's go back online. So our OBS software. But first, let's tech that. And you guys should be able to see that. Perfect. Let me quickly check comments to make sure everyone's. Yeah, we have to keep the same longitude for the geometry to work out for our problem. So 1 degree. So keeper of maps, you know some stuff. Of course you know this stuff. We've had conversations in the past. All right. So 1 degree is 60 nautical miles north, south. Perfect. So using that information, we can actually calculate. Then 5 degrees would be 300 nautical miles north, south. So we just need to multiply it by a factor of 5. Right. So you already have the answer here. So 1.85 avionic strict. I'm going to remember this. 1 degree is 60 nautical miles. That's actually very convenient. It's always interesting how things come in, factors of like 60, 180, 30. It's very nice that things work out that way. 60 seems to be a very important number in both time and, in measurements like degrees. But 1.85 kilometers. So we're just going to use Keeper of Maps. Because Keeper of Maps is a part of our team here. So we can use our information, but only north-south. Gotcha. That's interesting. Oh, but only I think I see the reason why, because as far as well, no. Do I see the reason why? Yeah. But I did not know that was a definition of I've heard of nautical miles before, but I've never known exactly what the math behind it is. But now I know. 1 degree is 60 nautical miles north south. I'll remember that. So it's equivalent to 1.85 kilometers for every 1 nautical mile. Oh, wait a second. Let me correct myself. So we need 5 degrees, which corresponds to 300 nautical miles. We need to use this conversion factor to figure out. All right, so let's go ahead and do that. Let's go ahead and calculate. So calculate distance between 2 locations. All right. So, and again, guys, the way in which we should be imagining this problem is that we're all in a group. We're trying to figure out how to determine the diameter of the Earth. All right. So we know that the locations are 5 degrees apart. So I'm just going to put D for distance. Has to be equal to 5 degrees. And I think I could do something like this for the degree sign. Maybe this might work. Let's check it out. Nope, it didn't like that. I'm going to be kind of lazy and put just like a O. Maybe that'll work for the degree. Okay, we're going to imagine that says 5 degrees, of course. I'm going to make that bigger so that we can see it better. All right, we're just going to imagine that's 5 degrees because I don't remember exactly what the proper phrasing for LaTeX is for the degree, the syntax is for getting the degree. All right. That's the reason why, because it's tighter together, the poles. Okay, that makes sense. Yeah, the spacings can become tighter and tighter. Good point. All right. Or all right. So 5 degrees. We need to multiply this times 60 nautical miles per degree. Right. So 60 nm. I would think nanometers, but that's nautical miles per 1 degree. So that should give us the number of nautical miles. And we need to multiply this times 1.85 kilometers per nautical mile. All right, guys, make sure my math is right there, because okay. All right. I think that this should work just fine. And I'm going to quickly throw in some brackets so that we know what we're looking at here. All right. That should be good. Perfect. And so what this should give us, and so I'm going to do 5, and I'm using my own very personal calculator on my laptop. You guys, of course, can verify that this is working out right, 1.85. And so I'm getting a very nice number, okay? Getting a number of, this is going to be units of kilometers, 555 kilometers is our distance. So D equals 555 kilometers. All right, so far so good. We know our 2 locations, and we now know the distance between our locations to be 555 kilometers. The next step, of course, is being able to measure the angle to Polaris. Now, I don't know exactly what the time zone you're in right now, but with my time zone, it's 12:30 now, roughly p.m. And there is no stars out right now because the sun in the atmosphere is making that impossible, right? So that's the reason why we're going to end up using Stellarium. Stellarium is going to kind of bring our group together to to 2 locations, actually. And there's one more key thing, if I'm not mistaken. The measurements need to be taken simultaneously. So going back to that diagram that I was showing earlier, where you have the 2 locations, you have to take the measurement simultaneously. All right. So my brain is dying on me right now. I want to go to Stellarium. That's right. So go to my OBS software. We're going to switch scenes, and we are now all together at nighttime. And I'm going to move my face up here. That's better. All right, so we're all together now, guys, at nighttime outside with our measuring device. Now, I believe when I did this experiment so long ago in undergrad during my observational astronomy course, I think we used a device known as a theodolite. Let me make sure that's correct, so that you guys can see what I'm seeing. I think it's called let's see, because I could be very wrong. Beyond, there we go. Yep, we use this thing. And so this thing, we use this to be able to make our measurement of the elevation or the altitude or the elevation angle of Polaris relative to our local horizon. Now, it's very important that we realize that at two different locations on Earth, local horizon will be different because of the fact that the Earth has curvature and it's not flat. If the Earth were flat, then our local horizons would all be the same. But because the Earth is not flat and it's curved, our local horizons are different. And we're going to see a very important thing here. The reason with the Earth being curved, us having different local horizons, the angle we measure should be different as well, right? So let's go ahead and see that. We go back to comments and make sure. Okay, there's one star out where you're at. Well, that's good actually. I have no. Well, I have a star out where I'm at too. Oh, wait a second. I got it. Me and you both have the same star out, probably. That being the sun. All right. So let's go ahead and go back to Stellarium. The very first thing we're going to want to do is we're going to want to navigate to that location on Earth. I wonder if I could just type in Ottawa. Let's see. I was already playing around with it. I need to switch the scene back. All right. I was already kind of playing around with Stellarium to kind of reacquaint myself with its features. Its many features. I'm not even too sure if they have a new version out. They probably do. But I've had this on my computer for quite some time now. So, Ottawa. Yep. Ottawa, Canada. There it is. All right. And so I want to make sure that it's actually showing the correct information. So north 45 degrees. Let's go ahead and look back at our at what we currently have. Make sure it's all the same. So that looks about right. North 45, longitude or latitude is 45 north, longitude is 75 west. If we navigate back to Stellarium, and I hope you guys can see this. Oh, what was that about? Okay. So somehow magically oh, I see what happened. I changed the location. Sorry about that. So it looks like everything checks out with what Stellarium's showing me here. 45, 24, 40. Give me a quick second. 45, 20. It's a little bit off. So I'm gonna modify this position so it agrees with what we currently are using for our location. So 45, 25, 31. So Philadelphia is about 5 degrees south of Ottawa. Yeah, it's 5 degrees north. But is Philadelphia on the same longitude though, or does it span such that it shares a common longitude? Because that's really the important thing here. Is Stellarium knows the sun is out in Ottawa. So actually, I've set Stellarium such that the time should be today, but the time is 9 o'clock p.m. tonight. So more or less, okay, one-ish. Okay, that's not too bad actually. When I did this calculation a long time ago, we had to account for the fact that there may be like a slight longitude difference or something like that. And when we were trying to propagate the errors. But today we're not going to be worrying about errors at all. So let's go ahead and get back to the problem. I'm going to modify this to agree with what we currently have. So 45, 25, and that very last part, 31.92. Give me 1 second. I think it's 39. Oops, that's not right. 0.92. 31. All right, and let me go ahead and correct the longitude now. 75, 41, 32.94. All right, and so this should show us. This should show us the appropriate information for this location. All right. So now what I can go ahead and do is exit out of this. I currently already have it pointing. I currently already have it pointing north. Okay. That was not expected. Sorry about that. Oh, it wants to follow my cursor. Oh, stop doing this. That is the star Polaris. For some good reason, I don't think that it actually said it properly. Give me a second. Let's see if I click on Ottawa, Canada. All right, so if I click on Ottawa, Canada, the lower left-hand side of the Stellarium window shows Earth, Ottawa, at 71 meters in altitude. Okay. If I click, that modifies. Okay, I think something is not right here. So let me make some adjustments. I'm going to minimize this. I need to be able to see everything. So let me make sure that you guys can still see what I'm seeing. All right. And so what we're going to do now, so I'll click a random spot. Let's see what happens when I now actually put the numbers back in. 45, 25, 31.92. It's actually 9188, but it should round it. Okay, so it did make the correction. All right. Yeah, because as of right now, it's currently set to 100 degrees west. So I need to still modify that. So 75 degrees west, 41 degrees, 41 degrees minutes, and then 32.94. But it should be 9352, but it'll round. There we go. All right, so now I believe it's in the proper location. Hey, Adam. Oh, wait, you're saying disengaging disengaging alert mode. Oh, that's funny. All right, so now we should be in the proper location. Good. So I can close this out. We're already pointing north. So now let's just go ahead and go to the star Polaris. And actually, finding Polaris, at least in Stellarium, is actually really easy. You just point yourself towards the north direction and look straight up. And you'll notice that there's one particular bright star up there. In the case of Stellarium, or if you have a phone, if you're actually outside at night, or even during the day probably too. If you're outside and you point your phone up towards the sky and you have some astronomical software installed on it, it'll show you exactly what stars you're able to look at. And it can do so even with the fact that the sun and clouds are out. So there's our star Polaris, and of course we're all huddled together. We're trying to use our device to measure the elevation angle at 9 o'clock p.m. at night. Um, there's actually really a funny story to tell when I actually did this, but I might save it for another stream. It involves shotguns though. Really weird, but so but yeah, we were still able to do our experiment though, and things came out nice. So, oh hi Larry, I see that you're saying hi there. So we got Polaris, and what we want to do now is look at the upper left-hand portion of our screen. Let's make sure you guys can still see what I'm seeing. Perfect. And we're going to want to now look for the line that says azimuth/altitude. So the azimuthal angle is it's 1, 2, 3, 4, 5, 6, 7, 8, 9. It's the 10th line down, and the apparent altitude is 45 degrees, 30 minutes, 56 seconds. So let's go ahead and get that information. And so I'm going to go ahead and switch scenes. I think this is this scene. Go back to tech. I really need to hurry up, or this might be one of those streams that kind of carries over. All right, so elevation angle or altitude of Polaris at location 1. And so we get an altitude measurement equivalent to altitude, and that altitude was 45, 30, 56. Copying and pasting is going to make this easier for me. So 45, 30, 56. And we'll need to convert this, of course, into decimal degrees. All right. So the next step, of course, is to determine the altitude of Polaris at the second location. Hey, Larry. So sorry. So let me update you on what's going on. So the idea for today's stream is for us to work together to calculate the diameter of the Earth. And the way in which we're doing this is kind of like a really old school method. So let's go back to the OBS software and switch scenes. We're basically using this image here to kind of help us with the calculation, where we're measuring the angle to Polaris from two locations on the Earth at the same time. But the key thing about these locations is that they share the same longitude, and we must know the distance between them. And so what we'll end up noticing is that there's going to be a difference in the elevation angle that we measure because of the fact that the Earth is curved. Our local horizons will be different as we're seeing in the image, and because our local horizons are different, the elevation angle, which is relative to the local horizon, will also be different for these measurements. All right, so let me quickly get back. So we're good here. We need to go back to Stellarium, and we now need to put in our second location. All right. So I'm going to move this over slightly. I'm going to minimize this so I can kind of see things at the same time here. And so our second location, which we don't really have a proper name for, but we know it's latitude and longitude, we'll go into Stellarium and we'll just go ahead and modify only the latitude because the longitude should remain the same for this calculation. So let's click that off. Let's make sure you guys are seeing what I'm seeing. All right, perfect. And so what we're going to do now is we're going to go to here And all we're going to do is change 45 to 50. All right. And it worked. Good. So now that we're at our new location, let's go ahead and get rid of that box. And now let's go ahead and navigate back to Polaris. And again, if you notice now, I haven't even touched the screen, but the star Polaris is no longer within view. And the reason being is because now that we went farther north, especially by 5 degrees, which is 555 kilometers according to our calculation earlier, Polaris will be much, much higher in the sky at this exact same instance in time. So all I have to do now is kind of pull the screen down. Let's do it slowly. Up, there's Polaris. All right, I'm going to click that. We're going to click on Polaris again. And what we'll notice now is that the angle for Polaris has changed. Its altitude. And so what we measure now is, and interestingly enough, we measure what appears to be. Well, let's go ahead and write it down actually. So I'm going to go ahead and go back to the the OBS software here. We're going to go back here. And I'm going to go ahead and copy and paste. And if I'm not mistaken, yeah, that does make perfect sense. The altitude angle of has changed by, it looks like it changed by 5 degrees, which makes sense because we're exactly like 5 degrees latitude up anyway. So let's go ahead and go back to our, well, let me go back. I'm going to go back to Stellarium and I'm going to copy this information. So it's going to be 50, 30, 44. Interesting. This is 44. It's that one changed actually. So 50 plus slightly by a few seconds. That's not much. So 50 degrees, 30 minutes, 44 seconds. Cool. Of course, we'll need to convert this information to actual degrees to make this work out properly. All right. Well, let's go ahead and do that actually. Now that I'm thinking about it, let's go ahead and do it. I'm going to go ahead and type that, and I'm going to scroll down. And this is kind of what we currently have. I'm going to make some modifications to the formatting. All right. So for this very first one, I am not going to worry about, even though I can do it, I'm not going to worry about making the calculation myself. We're just going to use an online resource. I'm seeing we're running out of... okay, never mind. Keeper Maps has done it for us. Perfect. I'm gonna use that value. 55.59-ish. That works for me. Or wait, did I get that? No, 45.59. 45.59. And for the other one, I'm just going to assume, of course, we're going to keep the 0.59. And this is going to be 50.59. It might be a little bit different, but that's cool. 45.52-ish. Thanks, Keeper of Maps. All right. Our team is rocking right now. We're totally like blazing through this. Suck it, flat Earth. All right. So now that we have all this information, the key thing now is to be able to set up a relationship that will allow us to calculate the diameter. And what we're going to do is we're going to use a proportionality. So the arc length formula, the simplified version of the arc length formula. So arc length formula. So again, if you guys run into, as Larry has already kind of like went towards, you run into some flat earthers. Show them this calculation, and then see what they have to say. If they deny that it's real, then that means that all of our information about geometry is kind of messed up. Then they got a really big problem there. All right. So arc length formula gives that the arc length, and I'm just going to put S for arc length. Oh, thank you for showing the calculation for how you did that. That conversion from degree, minute, seconds to decimal degrees. All right, so it's equal to R times theta. That's the arc length formula. But in our situation, calculating the radius directly would be nice. Which, I mean, I guess we could do it, right? But the key thing here is being able to calculate the diameter, which I could get from the radius. But what we're going to end up doing now instead is take the fact that we know the arc length, which is the distance between the 2 points, and taking into consideration that there's going to be an angular difference in our calculation to the angle to Polaris. That angular difference is due to the fact that the Earth is curved. And so what I'm going to do is I'm going to set up a relationship here, a proportionality, and I'm going to state, so begin align, end align. I'm going to state that I have a fraction, some s sub 1 over theta sub 1 is equal to some s sub 2 over theta sub 2. All right. Now again, now that I'm looking at this, it looks like we can actually just go directly from this relationship and go ahead and solve for the radius and then multiply it times 2 and we're good to go. But let's say that I didn't actually know that the equation was S is equal to R theta. I believe I should still be able to set up this proportionality that I have here, where I'm saying that the physical distance S1, I'm sorry, actually let's use D, because earlier I used D for distance. So I'm gonna change these to all D's. All right. So I'm saying some distance one, some D1, which represents the distance between our two locations, divided by their angular separation relative to the center of the Earth. Now note, this angular separation at the center of the relative to the center of the Earth between these two locations, we're able to get that information from the fact that the altitude measurements that we've made at these two different locations of Polaris are angularly separated themselves. So those angular separations are one and the same. And so I probably shouldn't have imposed. I imposed 5 degrees, but that's cool. I realize now that I probably didn't want to do that, but it's cool. Because when I did the experiment before, we didn't actually know the angular separation. But in this situation, me personally, I put an angular separation of 5 degrees. But that's okay. The math will still work out nevertheless. let's just go with the assumption that we didn't even know that I did the angular separation, that we just happened to be at that location on Earth and made the measurement. But 5 degrees is the angular separation. We know this. So let's go to the next line. And what I would want to do, of course, is solve for d2. Now, the relationship between my fraction on the left-hand side of the equation versus the fraction on the right-hand side of the equation is that d2 will represent the circumference of the Earth. And of course, we know that the circumference of the Earth is calculated by the equation circumference is equal to d times theta. Yeah, that's right. But in this case, I'm dividing the circumference by the angle theta. So really, it's almost like me stating that the radius calculation on the left-hand side of the equation is equal to the radius calculation on the right-hand side of the equation. If the math makes sense to you like that, at least that's how I'm seeing it right now. Let me go ahead and look at comments. Hey, Maddie. Oh, yes, Michael. That's exactly right. And I now realize by me like imposing what the angular separation is, I've kind of like I've personally, you know, not messed with the problem, but yeah. But nevertheless, the math will still work out. What you'd want to do is you'd want to find two locations on Earth where you know the diameter between the distance between them, and you don't know their angular separation relative to the center of the Earth. But it's all right. Okay. So I want to solve for d2, where d2 represents the circumference of the Earth. And so solving for d2, at some point I might actually have to put what that information, what these variables represent. All right, so I'll just take out d1. And this would be theta 2 over theta 1. And I'll put a note where d2 is the circumference of the Earth. S2 or S1. So I'm quickly making sure that for our notes that we know exactly what these variables represent. Or sorry, theta. So theta 1 and theta 2. So theta 1 is the angular separation that we get from the difference in elevations. But it's also the same thing as the angular separation of the relative to the center of the Earth for the two locations. But theta 1 is the angular separation calculated from difference in elevation angles or altitudes of Polaris. Relative to the two locations stated above. And lastly, and then there's theta 2. And theta 2 in this situation is going to be it's going to be 2 pi. And one more thing in D1. Sorry guys. All this typing is taking way too long. And D1 is the separation, or is the distance between our two locations. All right. And so now going ahead and solving for what the information that we currently have. Plugging this all in, we end up getting, so theta 2 is going to be, theta 2 is going to be 2 pi, or we could put it in degrees actually. That'll be more convenient. 360 degrees. And again, I'm using this O as like a degree symbol. And I think we calculated, or we don't even have to calculate because we already know, right? The angular difference between our altitude calculations. Now I'll scroll up here. Was like what, 5.02 degrees? $5.02. And lastly, the distance that we end up calculating for them was 555 kilometers. I'll scroll down and make sure that everything's looking properly. Down below. All right. And so I think that that's good so far. So we can go ahead and we can calculate what this value will be. So 360 divided by 5.02 times 555. And so we're now getting 39,800 point. And because we're using two decimal places, I'll keep it out to 0.8. And so our answer for D2 comes out to being, and this is in units of kilometers. So this is the circumference of the Earth. And we're going to round this to 0.8. We could stop here, but I ultimately said a diameter. And because the circumference is related to the diameter by dividing by pi, we could divide this by pi. So no indent. Calculate diameter of Earth. And we should get trying to type a little bit faster here because I realize now I'm over time by 6 minutes. All right. And so I'm just going to write this out actually. So D diameter. Let's put this in a text field. This has to be equal to D2 divided by pi. That's correct. I think that's correct. So D2 divided by pi. Let me quickly check comments because really, that would be so useful actually. See, this is one of the many new good things I'm hearing about Python actually. 32, yeah, divide this by pi, which is which we can use 3.14. I'll use that actually, 3.14. The other number you can use is the fraction form, which I believe is 22 over 7. But we're just going to use the decimal number and see what we end up getting. So I'm going to go ahead and calculate this on my own computer here. So 39,800.8. And this should be divided by pi. And we get 12,000. And the value that we get is here. This should be 0.99 kilometers. I hope this is right. So this is our final answer. The diameter of Earth should be roughly equal to 12,668.99 kilometers. It's somewhere nearby. I'm pretty sure there's going to be some rounding errors in there, but let's go ahead and check our work. Unless you guys have already checked it, let's go ahead and see if this is correct. So let's switch scenes. Let's go back to here, to Google, and I'm going to put in diameter of Earth in kilometers, because that's the units we're using. All right, 12,000. Let's make sure you guys can see what I'm seeing here, actually. 12,742 kilometers versus our guess, or our estimate, of 12,668.99 kilometers. I think we did a pretty good job. At least we're on the same order of magnitude. And we're fairly close, actually. Maybe even in the next stream, we can use that time to like kind of go through the errors involved with this calculation, and as to how those errors would show how much close we are. Well, include errors to be able to show if our errors include the correct value. We might be able to do that with our next stream. But guys, thank you all for joining. Indeed, well done, team. It was a good job, guys. So thank you guys for joining. And I'll be back on Wednesday as well as Friday. And so I look forward to talking science with you guys again. Keeper of maps, you are not the source of error. If that's the case, we're the source of error because we all work together. All right, guys, I have to go now. So thanks again, guys. I will see you guys Wednesday, 12 o'clock Central Time. All right, bye.